So we have seen in the course of steel structures the different types of steel structures which we will be dealing with, mostly the buildings. And in your syllabus, as far as your syllabus is concerned, uh, you are supposed to design various members of a given structure. And as far as complete structure is concerned, in that case, you are only supposed to analyze, not design. Analyze uh, the truss type of structure. And we have seen the difference between analysis and design. Analysis is something which is related to the application of load on a given structure, and with the help of this application of load, you are supposed to find out certain values. Those will be essential in your design. That is nothing but broadly you will say that the output result of analysis is nothing but bending moment shear force values. With the help of these values, then you are supposed to design various components. The term design, we refer it to finding out the dimensions and the quantity of the given material which will be required for design purpose. So exclusively we will be using steel, and we will be designing the components of any given structure with the help of structural steel. And as far as structural steel is concerned, we also saw that there are different types of shapes like the T, angle, box, H section, I section, channel section, etc. Widely used are I section, angle section, channel section. Sometimes, based on the requirement and the loading condition, we need to fabricate the different types of cross section. For example, with the help of four angle section, that is this one angle, in addition to this one angle, you will have to make use of three more angles in such a way that a box shape is obtained, something of this sort. But in that case, nothing will be monolithic. That means this will be a separate angle section, another angle section will be somewhere here, another angle section will be here, and last will be here. So a kind of box section is prepared. Also, you may come across two channel sections. If they are placed like this, then again you can see that a box is available with you. Okay. So depending upon the loading condition and depending upon the advantage of such kind of box sections, keeping in view those values or those parameters, we are supposed to modify these sections. So these are, you can say, the broadly available cross section in the market, and we are supposed to make use of such type of cross sections in order to prepare any structural steel or the steel structure. Next, we have also seen the different types of steel. Okay, and widely used is the mild steel. For mild steel, this is the stress strain variation, whose application we have seen over here in this case. But before this, what we have seen? We have seen the various design philosophies which are available. So once we say that we are designing any component, we need to consider some design philosophies. Very widely used are working stress design and limit state design. Plastic design method is used for very particular cases. If the structure is determinate, then plastic method can be easily used. But owing to the different advantages of limit state design method, we shall be using limit state design method. And in order to understand what is given in the limit state design method, we need to first of all understand the stress strain variation of mild steel. Based on that, further discussion is being made. Okay, so we I had just introduced this variation of stress strain curve. I have also told you about several assumptions those are made in order to simplify this curve. Simplify in the sense you can see that this is a non-linear type of curve, and if anyone wish to find out any value pertaining to this non-linearity, then it is difficult to identify. So in order to simplify things, the researchers, what they did, they considered this lower yield point to be the yield stress, that is Fy, and they have extended this line up to the fracture limit. They term this curve, which is a bilinear curve, to be elastoplastic stress strain curve. This is elastic zone, this is plastic zone, and this plastic zone they have assumed to be continued up to the fracture. And while assuming this, what other assumption they have considered? That means it is completely valid as far as the experimental results are concerned. So if we, this is actually the stress strain variation for tensile test. Similar variation can be observed for the compression test also, and therefore whatever stresses are developed, uh, if if a steel member is subjected to force, whatever for its stresses are developed in the compression side, those will be same or similar on the tension side. Based on this assumption, what we have studied, we have considered this I section. As you can see in this figure, this is an I section, and in this I section we have got flanges. This is the top flange, this is bottom flange, and this is the web portion. If we apply moment or couple, or even if we apply centrally applied load for this simply supported beam, the variation of the stresses can be found in this manner. With small increment of the load, the stresses in the compression flange will be developed, which is shown in the red color, and you can consider the variation of these stresses to be like this. And over here, what do we observe? That since these red marks are only restricted to the flange, the elastic limit or the elastic stress, or what you can say the yield stress, is achieved. So you can see the variation is linear. You can call this to be stage 1 loading. Okay, stage 1 loading, and the stress strain variation can be found out to be like this. If we increase the amount of loading, then what do we observe? These stresses, they extend from the flange portion up to somewhere over here, the web portion. And this is not just true for the compression phase, this is true for the tension phase based on the assumptions what we have made. In this case, what will happen? The physical meaning of the this figure, that is the second condition, wherein the green stresses are developed on compression as well as the tension side. The physical meaning of this is that these stresses are now into the plastic zone. They have entered into the plastic zone, and you can see condition 2, or the loading condition part 2, it can be correlated with this condition. That is, some part of the web is getting affected with this stress, both in the compression as well as the tension side. Okay. So what is the variation? It is something of this sort. Now, if you consider the engineering curve, or whatever curve we obtained from the actual test, if I try to compare this situation, that means the stresses have entered the web portion, you can assume that somewhere this is the point, and I want to plot this variation over here. So first of all, it becomes difficult to identify the curve, what the degree of the curve, isn't it? So, and after even if we try to identify that curve, degree of the curve, then it will be difficult for us to plot over here the non-linearity, and because of which the researchers, what they did, or the scientists, what they did, they considered this to be a straight line, so that over here the variation will be again linear. Okay, and then finally we will apply the amount of load increase the load in such a way that these stresses are developed in the tension, in the compression as well as in the tension phase, and we will achieve a point wherein the cross section of the section uh, is reduced drastically, and with the further increase in the loading, at this point there will be a failure. This point is known as hinge, which is commonly known as plastic hinge. Why plastic hinge? Because at this point you can see this stress, whatever stress is developed, this is related to plastic zone. Okay, and therefore the associated hinge is known as plastic hinge. The beauty of this plastic hinge is that one axis is developed which is known as equal area axis, in the sense whatever area which is on the compression side and tension side, both these areas are equal about this axis. It is different than neutral axis, because if the cross section is symmetrical, then in that case neutral axis will be equal to equal area axis. But in case of unsymmetrical type of sections like the T section, or even in the even in this I section, if one of the flanges is more or less, in that case also you will find the asymmetry condition will be developed. Got it? So this is the variation of stress strain curve, and uh, based on the loading condition, we may achieve one plastic hinge, and this plastic hinge formation is very important for our study, further study. Okay? So fine, I will just open this video, and we will discuss this video after some time. Okay, let it open. Okay. So this is the same explanation in terms of the stress strain curve. Okay, same explanation has been done. So you can see over here, this is stage 1, where the flanges are yielding and the stresses are developed. So yield stress is developed over here, and similarly the strain variation. So in this case, the strain value is greater than the yield strain value, right? Then slowly it has reached to the web portion. Over here also you can see the variation. Over here what has happened? Yield stress is already there, but it has gone beyond that yield stress value and it has entered into plastic zone condition. And over here the plastic hinge formation is seen, it is observed, and you can see the area on the compression side and on the tension side both are same. So this becomes the equal area axis. Now in your IS 800 2007, instead of the stress strain curve, uh, moment rotation curve is discussed. So what is moment rotation curve? You can see it is similar to the stress strain curve only. Okay, and the moment versus rotation values can be obtained from this figure. So can you see the simply supported beam? The simply supported beam is loaded with some centrally applied load, and you will expect the deformation of this beam to be in this manner with this application. Also, if you go on increasing the amount of P over here, so you will expect with the increment of the load, moment will also increase, as well as the rotation associated to that moment, it will also go on increasing. Okay? A typical moment versus rotation curve. This is the what you can say actual experimental curve, you can say. Okay. See, the behavior is again same as your stress strain variation. Only the thing is the values may be different, and though the representation of the values is in the term of moment and rotation values. Okay. So now over here Again, in order to simplify this curve, because again, here the nonlinear variation can be observed. So in order to avoid this nonlinearity, again, such kind of modification has been done, wherein you will find bilinear curves. So again, this is idealized moment rotation curve. And you can see now, what is the notation? My. My is nothing but the yield moment. And this yield moment is nothing but equal to MP. MP is known as the plastic moment. Plastic moment Q, because you can see over here at this point, after the increment of moment, this curve has entered into plastic zone. And for simplifying the matter, this has been extended up to the failure point, right? M suffix M consists of the maximum of flexural strength, maximum bending strength, or maximum flexural strength, maximum flexural capacity. Okay? So these are the terms which IS 800-2007 has incorporated instead of the stress strength curve. That is the only change. And with respect to this, you can see the rotation associated to the plastic moment. It is known as plastic rotation, sorry, defined by theta p, and theta u is the ultimate rotation capacity. Okay, that means at this location, the failure occurs, theta u. Okay. Now, based on the complete stress strain variation and moment rotation curve for beams, listen very carefully what I am saying. For beams or horizontal member, or the members those are subjected to flexure, bending, for such type of situations, one term is defined in your IS 800-2007. What it is known as? It is known as classification of cross section. Can anyone please tell me what this classification of cross section may be? What do you think of? So as a beginner, if I ask anyone, what do you understand by classification of cross section? See, this discussion is very important for the further classes. If you don't understand this term right now, then it will be difficult for the other coming classes. So please let me know what what is your first impression when I say that. What do you understand by the term classification of cross section? So this is just a discussion. You please tell me what do you understand by classification of cross section?
The different cross-section we can observe in terms of shapes.
In terms of shapes. Okay. Anyone?
Different parts.
Please come again. I didn't get you.
Different parts.
Different parts. Okay. Anything else? So, in general, the first impression when we say that we need to define or we need to explain classification of cross section. So, what comes in our mind? The different shapes. Am I right? यही आपके दिमाग में आया होगा. And one of the students has already told me that it is related to shapes. Forget about that. This is not related to the shapes. Okay? This is not related to shapes. It has got one term which is known as classification. And this classification doesn't talk about shape. Am I clear? Now I will be explaining you what exactly this classification is all about. Okay? So have you understood the first impression, whatever first impression we have related to the classification of cross section? That is, it is not asking about the shapes. We are not supposed to discuss about I section, I cross section, channel or C cross section. No, this is not related to that. Whatever you have told me, that is the type of sections. This is not the classification. Classification is something else. The term of classification, or if we try to define classification term, it is related to the overall behavior of anything. Okay, are you getting me? So classification is based on behavior of given material. It is not related to the different shapes. क्रॉस सेक्शन इसलिए कहा गया है इन लोगों ने because over here the cross section is pertaining to the type of section, that is whether it is a beam member, whether it is a column member. Okay, right now we are discussing about horizontal member, that is beam. ये ध्यान में रखो, whatever discussion we are doing, this is with respect to the flexure member or a member which is subjected to bending. Got it? So now let's speak about what is classification and why this term has been introduced in your IS 800 2007. So as you can see over here, uh, representation of moment versus rotation curve. This has been taken from Design of Steel Structure and Subramanian book. This is one figure which is represented in that book, and you can see now. Just try to understand what exactly is the classification of cross sections. Classification of cross section depends upon the behavior of the material at various different stages. तो हमने देखो 3 स्टेज हमने स्टडी किए. What were the stages? These are the 3 stages: first, second, and third. Okay, you remember these things, right? In the first stage, what did we observe? That the material has yielded up to its yield stress value, that is Fy value. This is stage 1. What is the second stage? With the further increase, the capacity has increased. With the further increase in the load, the capacity of the material has increased, in the sense it is able to sustain the load up to this limit. Are you getting me? It is able to carry that load up to this limit, and here also you will find that there is no failure. Got it? Are you getting me?
Yes.
There is no failure as such. Okay? Then with the further increase in the load, again it has reached beyond that plastic limit, and it has reached up to this point wherein you will observe with the further increase in the loading, it will collapse or plastic hinge will be formed, right? So based on these 3 variations or these 3 stages, this curve is now useful for our classification purpose, right? So classification is what? It is nothing but the behavior of the material at different loading stages you can consider. Similarly, based on the description of classification, you can now understand that there are 4 different classifications. Those are made by your IS 800 2007. These are class 1, which is known as the plastic classification of cross section or plastic behavior. Second is compact, which is nothing but class 2. Third is semi-compact, which is class 3. And fourth one is slender, which is glass 4. ठीक है? Meaning of this is, try to understand, these plastic cross sections are those type of cross sections wherein you will find the behavior of this material to be in this manner. That is, the material has first of all yielded, yield stress has been achieved, and it has the capacity to even carry the load up to the point at which plastic hinges are developed. That stage or that behavior is known as plastic classification. Getting me? Then second is the compact. In this stage, what happens? The material has fully yielded, okay, and it has also reached to the plastic zone, but it is yet to reach the plastic hinge formation, and before reaching the plastic hinge formation, it has failed. So this classification is known as compact, or it is also known as class 2 classification. So if I want to explain semi-compact, can anyone tell me based on this variation what it can be? What it should be? क्या हो सकता है semi-compact? Just give it a try. If you have understood this thing, these two stages, can you please let me know what should be over here? What should be the situation as far as semi-compact classification is concerned? क्या हो सकता है?
Just was the link.
Yes, and beyond that, it is not able to go even into the plastic stage, as you can see, and it fails. ठीक है? And what about slender? Slender classification is the worst. Why? Because it has not yet reached to even its yielding point, as you can see over here. This stage is well below the plastic zone, sorry, rather the elastic zone. Elastic limit तक भी नहीं पहुंचा है वो, and over here itself it fails. And somewhere you will find the working stress method design. You know, it revolves around this slender classification, which is actually not good, because over here what will happen, in order to avoid the failure situation, we will try to design uh, that member in such a way that it will become bulky. More amount of material will be required in order to sustain the load, whereas over here you will see the amount of material which will be used will be comparatively less. Here it will be further less, and here it will be the least. So somewhere we are heading towards, economy slowly, but keeping in view the with all the technical details. So have you understood the classification? And this classification of cross section, it depends upon this moment rotation curve, and somehow it is related to the stress strain variation. Is this okay?
Yes.
Huh? Have you understood to some extent? So
Yes.
yeah, so fine. But while defining this classification of cross section, first and foremost thing you should remember that it is not the shapes, it is not the type of shapes. I am repeating, it is not the types of shape, क्योंकि इस पे क्वेश्चन पूछा जाता है. It may not be only your written, it may be your oral also, that is viva voce. In that also you may be asked with this question, what do you understand by classification? And most of the time students, they repeat this thing that it is, the shapes. Actually it is not. Classification, it depends on the behavior of that particular cross section. So have you understood this thing? Okay. Now there are few things which you need to remember. First is, I mean, before defining these behaviors or classifications, you need to understand that the web slenderness ratio is such that its buckling before yielding is prevented. Okay, I will let you know what is the slenderness ratio. Slenderness ratio is nothing but the aspect ratio. Have you ever came across this term of aspect ratio? Do you know what this aspect ratio deals with? Aspect ratio, you can say, the ratio of largest dimension to the smallest dimension. That is the aspect ratio. And what it says that the web slenderness ratio is such that its buckling before yielding is prevented. That means uh, the vertical web, whatever vertical web we have, okay, that should not fail before yielding. At least it should yield. It should not fail before yielding. That means this condition should not take place earlier. So these are the assumptions in order to define this behavior. Okay. Second assumption is, since this classification is based on bending, it cannot be used for compression members. So that's why I have been repeating that whatever discussion we are doing, this is with respect to beam or a member which is subjected to a member which is subjected to flexure. Okay, so this classification whatever I have discussed, this is true only for beams. Similar type of classification of cross sections should you will observe when we will be discussing about the column. Okay, so classification of cross section for beams and for columns, these two things are different. Although they are different, you will find there is some similarity that I will be discussing later on. Okay, so have you understood this thing? Then third point is, only plastic and compact section should be used in limit state design. So when it comes in terms of designing, so it is a very genuine question that which classification or which behavior should we consider in order to design any member. So as far as IS 800-2007 is concerned, it says that compact and plastic sections are sufficient enough to go for the design. We should not think of semi-compact section or slender section, right? So we will slowly see whenever we will be solving numerical. In that case, we will observe that uh, you will have to design the members in the compact and plastic types. If for because of some reason or the other, if our design comes in this range, then we are supposed to redesign it and we are supposed to go to compact or plastic. That we will see how to do it. Okay, there are a few more things, few more considerations which we are supposed to do later. The class of cross section is determined by the lowest class of all its constituent elements. Okay, that is the, it will depend upon the thickness of the material, right? Fine. So have you understood this thing to some extent? Yes. Okay, so don't get confused. Classification is behavior, it is not the cross section types. Okay, fine. So let me see whether these videos are on. Okay, ये थोड़ा बड़ा है. Are you able to see this screen? Video दिख रहा है आप लोगों को?
Yes.
Okay. Now you can see over here. Wait. There is one phenomena which is known as local buckling. Acha, before local buckling, can you please let me know what do you understand by the term buckling? What is your understanding related to the term buckling? क्या होता है? Yes, buckling यानी क्या होता है?
Bending
नहीं
and changing shape.
नहीं बेटा, bending and buckling, these two things are different. So you cannot mix these two things. क्या हो सकता है buckling? अच्छा, bending क्या होता है? Both these things are actually deformation. Do you agree? Bending or buckling, these two things are deformations, isn't it?
Yes.
So, so if I say, if I want to define bending, actually bending is nothing but that deformation of any member which is in the direction of the loading applied on that member. Don't you feel so? Let's say, for example, simply supported beam. It is carrying uniformly distributed load. How is the direction of that loading? Vertical. And how is the deflection? It is again vertical. Am I right?
Yes.
So the profile, depending on the profile, it bends. And therefore we call this as bending phenomenon. However, if I want to define buckling, so if the deformation of a member is perpendicular to the direction of the loading, in that case we will say that member buckles, or that distortion or that deformation is known as buckling. Have you understood this this very difference between bending and buckling? समझ गए आप लोगों को?
Yes. Can you please repeat for buckling?
Buckling is nothing but the deformation which is perpendicular to the loading. So just imagine column, and that column is, let's say, hinged at both the ends. ठीक है? And vertical reaction forces are developed at the hinge. बराबर है? Forget about the horizontal reaction forces. Only vertical reaction forces are developed. By the virtue of these vertical forces, how is the distortion or how is the deformation of the column? Don't you feel that it will be in the perpendicular direction? Perpendicular direction of the loading. बराबर है? So let's say I will try. ये देखो, ये vertical column है, मान के चलो vertical column, and these are the loads which are applied like this. So with the help of this, how it is going to deform like this? And with respect to these loadings or whatever forces, how is the deformation? It is perpendicular in direction. Correct? So this is what is buckling all about, right? So buckling, you will expect that it will occur only in column. So this is not true. It is not true. Buckling may be in the beam also. For that, we should see this video. Okay, and that buckling is known as local buckling. So can you see this beam over here? This beam is actually subjected to different forces or loads. So these are the loads. The plan which is uh, showing these loads can be seen over here. So this is the beam cross section, you can say. This is I cross section. These are the dimensions. Okay? And these are the loadings which are applied. And this is a simply supported beam which they have assumed. Okay? At these locations, how is the nature of the load? It is vertical. Okay, and now what happens? Just try to see. What do you observe? With the application of the loading, this has bent. बराबर है? Bending. Can you see the bending?
Yes, sir.
Right. Now just observe what has happened to the top flange. Okay, just observe. ठीक है. What do you observe as far as this top flange is concerned? क्या हुआ है? What do you observe? ये देखो क्या हुआ है? This is the plan and this is the elevation. ये flange का top view है ये. So what do you observe in the flange? That flange was it was very plain. Initially it was plain. Now can you see some sort of distortions? Those have taken place with the application of the load. Can you observe these things?
Yes, sir.
So this is known as local buckling phenomena. In the sense, although the load which was applied on this complete cross section was vertical, however, the distortion which took place, it is perpendicular to the direction of the loading. And in beams, especially the steel structure or the structural steel, you will find such kind of phenomena to be very predominant, and this is known as local buckling effect. This local buckling you can observe not only on the top flange, but with the increment in the loading, you may even observe in the bottom flange of the I section. So have you understood this? First of all, have you understood the basic difference between bending and buckling? Okay. Okay. Once you have understood this, then you must also understand that the difference is not only restricted to the beam or column. Even in case of beam, you may come across buckling effect. Although you can see the loads are acting in the vertical direction, right? So this is known as the local buckling phenomena. And if you have understood this local buckling phenomenon, now I will come back to this slide over here. In case of classification of cross section, in your IS 800 2007, it is written that you will obtain such kind of moment versus rotation curve only for some specific conditions. पहला condition तो ये है, web slenderness ratio is such that its buckling before yielding is prevented. ठीक है, ऐसा मेंबर अगर अवेलेबल है तो ही हमको ये फाइनल मोमेंट वर्सेस रोटेशन कर्व मिलेगा, और इसी से ही हम लोग उसका बिहेवियर और क्लासिफिकेशन डिफाइन कर पाएंगे. ठीक है, फर्स्ट केस इज दिस. सेकंड इज द मेंबर should be such, or all the different members of that cross section should be such that they should not fail in local buckling. ठीक है, local buckling you may observe local buckling phenomena over here. ठीक है, so देखो इस केस में क्या हो रहा है, कॉम्पैक्ट सेक्शन में it has completely yielded, it has also reached up to its plastic limit, but it is unable to reach up to plastic hinge formation, that is failure point. It has not yet reached. Before that it has failed. And what must be the reason of failure? Local buckling effect. ठीक है, local buckling is very dangerous. It can fail the complete cross section or the complete member before yielding, before achieving the plastic hinge. And you can see where the plastic hinge has been generated. It has been generated at this point, that is exactly at the center of the web. Before achieving this, if your flange itself it fails, then the contribution of this cross section has no meaning, isn't it? So compact sections are those where you can expect some amount of local buckling phenomena that can that have taken place. Similarly, in case of semi-compact section, what has happened? It has reached up to its yield stress value, but it is unable to reach into the plastic zone. Why? Because of the presence of local buckling. Got it? And ये जो slender जो hopeless sections जो है, इसमें क्या होता है कि जो yield stress value है, ये अचीव ही नहीं होती है. Why? Because of the presence of the local buckling phenomena. And it is not necessary that only after providing heavy loads you will come across the local buckling phenomena. Even with the help of smaller loads also, sometimes it may happen that the sections are very poor, based on which the local buckling can occur in the earlier stage itself, and those sections are our slender sections. We want to avoid all these things. That means we are supposed to avoid the local buckling phenomena initially in order to achieve this two stages or two behaviors. Have you understood this thing to some extent? ठीक है? So I hope you have understood the meaning of classification of cross section. First of all, you have understood the basic difference between bending and buckling. You have also understood the term local buckling phenomena, and this local buckling phenomena can occur at any point of time. We want to avoid it. How it should be avoided? What are the various assumptions? What are the various procedure methods in order to avoid local buckling? That is completely given in your IS 800 2007. Slowly we will go into the details of those. But before that, I hope that you have understood this thing. Am I okay with this?
Yes.
Okay. In case of any difficulty, feel free to ask. I will clear your doubts. But this thing should be very clear. Okay? And I will be sending you this complete PowerPoint presentation once I finish the discussion. Okay? Till that time, I expect that you people should go through some literature, go through some books, reference books, whatever I have told you. Even you should refer the IS 800 2007. And in case of any difficulty, we can discuss things. Is this okay?
Yes.
Okay, so I will stop over here, and in the next class we will see the next part. Thank you.